In March of 2025, a team of Chinese physicists published a paper in Physical Review Letters, one of the most respected peer-reviewed journals in all of physics, announcing that their newest quantum processor had achieved something genuinely extraordinary, a computation completed in a matter of seconds that would take the world's most powerful classical supercomputers roughly a quadrillion times longer to match, and a result that outperformed Google's own earlier benchmark quantum chip by a factor of 1 million. This is a real, verified, published claim, not an internet rumor. And understanding exactly what it means, what it doesn't mean, and how it fits into the broader, ongoing race between the world's leading quantum computing labs is genuinely one of the more fascinating stories in technology right now. The chip at the center of this story is called Zuchongzhi 3.0, developed by researchers at the University of Science and Technology of China, working in cooperation with roughly half a dozen additional Chinese scientific institutions, under the leadership of physicist Jianwei Pan, alongside colleagues Xiaobo Zhu and Chengji Peng. It's a superconducting quantum processor, meaning it uses the same basic underlying hardware approach as Google's own quantum chips, tiny circuits made from superconducting materials, cooled to a temperature colder than deep space to preserve the fragile quantum states the whole system depends on. Zuchongzhi 3.0 integrates 105 qubits and 182 connecting couplers onto a single chip, a genuinely substantial increase in both scale and engineering sophistication compared to its predecessor, Zuchongzhi 2.1, which had operated with 66 qubits back in 2021. Let's get the specific numbers exactly right, because precision matters enormously here. And it's exactly the kind of detail that separates an accurate, verifiable science story from a garbled internet rumor. The USTC team ran Zuchongzhi 3.0 through a specific benchmark task called random circuit sampling, using an 83-qubit, 32-cycle configuration, a task deliberately chosen because it plays directly to quantum computing's core strengths, while being almost impossibly difficult for a classical computer to simulate directly. The team reported that their chip completed this task at speeds roughly 10 to the 15th power, 1 quadrillion times faster than the most powerful classical supercomputers currently available. Separately, and this is the specific comparison your title is referencing, the team reported that Zuchongzhi 3.0 outperformed Google's Sycamore processor, the chip used for its original headline-making 2019 quantum supremacy claim, by a factor of 1 million. A gap the researchers described as 6 orders of magnitude. It's important to be precise about exactly which Google chip is being compared here, because getting this detail right actually matters quite a bit for understanding the full picture, and it's a distinction that a lot of casual coverage of this story tends to blur together. The specific million times figure refers to a comparison against Google's Sycamore chip, the 53-qubit processor Google used back in 2019 for its original groundbreaking quantum supremacy demonstration, the experiment that first showed a quantum computer could complete a specific task. In that case, in about 200 seconds, that would take a classical supercomputer roughly 10,000 years to replicate. Sycamore was, and remains, a genuinely historic piece of hardware, but by 2025, it represented an older generation of quantum computing technology, roughly 6 years old by the time Zuchongzhi 3.0's results were published, a considerable stretch of time in a field advancing as rapidly as quantum computing has been. This matters because Google had, by the time this Chinese paper was published, already moved on to a considerably more advanced chip of its own, Willow, unveiled in December of 2024, just a few months before the Zuchongzhi 3.0 results came out. Willow itself demonstrated a separate, and in some ways even more significant, computational advantage over classical supercomputers, along with a genuine breakthrough in quantum error correction that we'll get into shortly. Live Science's coverage of the Zuchongzhi 3.0 results was careful to note this exact distinction, describing the Chinese chip's overall performance as rivaling, rather than definitively surpassing, the benchmarking results Google had already set with Willow just months earlier. In other words, the honest, complete picture is that Zuchongzhi 3.0 achieved a genuine million times speed advantage over Google's older Sycamore chip specifically, while its performance against Google's newer Willow chip looks considerably closer to a genuine head-to-head rivalry between two of the most advanced quantum processors on the planet, rather than a clean, decisive victory for either side. It's worth walking through the actual engineering improvements that allowed Zuchongzhi 3.0 to achieve this leap, because the underlying physics is genuinely impressive on its own technical merits, well beyond the headline speed comparison. The USTC team reported a parallel single-qubit gate fidelity of 90%, and a parallel 2-qubit gate fidelity of 62%, essentially measures of how accurately the chip can perform its basic quantum operations without introducing errors. For context and fairness, it's worth noting that Google's Willow chip actually edged out Zuchongzhi 3. 0 slightly on these specific fidelity metrics, posting figures of 99, 97% and 99, 86% respectively, meaning that on this particular narrow measure of raw operational precision, Google's newer chip still holds a modest technical edge. The Chinese team attributed their own improvements largely to advances in fabrication methods and qubit design, including a notable shift to using tantalum and aluminum in the chip's construction, bonded together using an indium bump flip chip process, materials and manufacturing techniques specifically chosen to improve accuracy and minimize the kind of contamination that can degrade a qubit's performance, changes that reflect the kind of steady, incremental materials, science progress that has genuinely characterized much of the recent advancement across the entire superconducting quantum computing field, not just at USTC specifically. It's also worth spending real time on what random circuit sampling actually measures, and being honest about its genuine but narrow significance, because this exact benchmark has become the standard yardstick both Google and China's leading labs keep returning to, and understanding why helps explain both the genuine excitement and the legitimate skepticism surrounding results like this one. The task works by running an extremely complex, carefully structured sequence of quantum operations across the chip's qubits, and then measuring the resulting probability distribution of outcomes. Because of how quantum superposition and entanglement work, tracking that distribution requires accounting for a space of possible quantum states that grows exponentially larger with every additional qubit, a computational burden that becomes genuinely, provably intractable for classical computers. Once you're dealing with enough entangled qubits, which is precisely why this specific task produces such staggering speed comparisons, it's a deliberately, almost artificially difficult problem for classical computers, chosen specifically because it showcases quantum hardware's core structural advantage as clearly and dramatically as possible. That's also exactly why serious, careful coverage of this result, including reporting from outlets like the Quantum Insider, has consistently included an important caveat alongside the headline numbers: random circuit sampling. However genuinely impressive the speed comparison, doesn't directly translate into solving practically useful, real-world problems. It's specifically designed as a benchmark, a way of demonstrating and measuring quantum computational advantage in as clean and unambiguous a way as possible, rather than as a stand-in for the kind of broader, general-purpose computing tasks quantum computers will eventually need to tackle if they're going to deliver on their much-discussed potential for drug discovery. Materials science, cryptography, or optimization problems. That's not a criticism unique to the Chinese team's work either. It's the exact same honest caveat that applies equally to Google's own Sycamore and Willow supremacy claims, since all of these headline-grabbing results have used essentially the same category of deliberately quantum-favoring benchmark task. There's also real important historical context worth including here, because quantum supremacy claims, however genuine at the moment they're announced, have a well-documented track record of narrowing over time as classical computing techniques improve, and being upfront about that pattern is exactly what separates careful, trustworthy science. Reporting from uncritical hype. When Google first announced its 2019 Sycamore supremacy claim, the company estimated the classical comparison task would take roughly 10,000 years on the era's best supercomputers. That estimate didn't hold up unchallenged for long. Researchers, including a team at IBM, subsequently developed improved classical simulation algorithms and demonstrated that a sufficiently optimized classical supercomputer could actually complete the same benchmark task in a matter of days rather than 10,000 years, dramatically narrowing Google's original estimated gap. This pattern, an initial dramatic quantum advantage claim followed by classical algorithms partially, though rarely completely, closing the gap through cleverer simulation techniques, has repeated itself multiple times across the field's history. And it's a genuinely important, healthy part of how this area of science actually operates. It doesn't mean the underlying quantum hardware achievements aren't real or significant, Zuchongzhi 3. Zero's engineering improvements in gate fidelity, qubit count, and material science are entirely real and independently verifiable, regardless of how the specific classical comparison numbers eventually shift. But it does mean that any single quadrillion times faster or million times faster headline number should be understood as a snapshot of a particular moment in an ongoing, evolving competition between quantum and classical computing approaches, rather than a permanent, unchallengeable final verdict. It's worth situating Zuchongzhi 3.0 within the broader arc of China's quantum computing program, because this result didn't emerge in isolation. It's part of a sustained multi-year research effort that has been steadily building toward exactly this kind of milestone. USTC's Zuchongzhi program has been progressing methodically for years. The team's earlier Zuchongzhi 2, one chip, unveiled in 2021, operated with 66 qubits, and had already demonstrated genuine quantum computational advantage using an approach broadly comparable to Google's original Sycamore demonstration. Separately, in 2023, Chinese researchers demonstrated a different kind of quantum supremacy claim entirely, using a 255-photon photonic quantum processor, a fundamentally different underlying technology from the superconducting approach Zuchongzhi uses, that reportedly surpassed the fastest classical supercomputers by a factor of 10 to the 16th power, an even larger gap than Zuchongzhi 3. Zero's headline number, demonstrating that China's quantum computing research isn't concentrated in a single approach or a single lab, but spans multiple genuinely competitive technical strategies pursued in parallel across different Chinese research institutions. There's also a meaningful technical distinction worth drawing between Zuchongzhi 3, Zero's specific achievement, and Willow's, because they actually represent somewhat different kinds of milestones, even though both get compared under the broad umbrella of quantum supremacy. Willow's headline achievement, alongside its own random circuit sampling speed benchmark, centered heavily on a genuine breakthrough in quantum error correction, demonstrating for the first time, with solid experimental backing, that adding more physical qubits to a properly designed error-correcting code could make a quantum system's overall reliability improve exponentially rather than degrade, a 30-year theoretical goal finally confirmed with real data. Zuchongzhi 3. Zero's announced results, by contrast, centered primarily on raw computational speed and gate fidelity improvements on the random circuit sampling benchmark specifically, rather than an equivalent independently headline-grabbing error correction milestone in that particular paper. That's not necessarily a knock against the Chinese team's work. Different research groups often choose to prioritize and publish different specific technical achievements at different points in their broader research programs, and USTC has separately pursued its own error correction research as well. But it does mean that directly comparing which chip is better isn't quite as simple as lining up two single headline numbers side by side, since the two teams have, at various points, chosen to highlight somewhat different technical accomplishments as their primary public benchmark. It's worth spending a moment on the genuinely serious, credentialed scientific team behind this specific result, because it matters for evaluating how seriously to take the claim. Jianwei Pan, the lead researcher on the Zuchongzhi program, is one of the most prominent and internationally respected quantum physicists in China, credited with a long track record of genuinely significant, independently verified contributions to quantum information science, including pioneering work in quantum satellite communication and quantum teleportation experiments that predate the Zuchongzhi chip program by years. This isn't a fringe or unverified research effort. It's work published through completely standard, rigorous scientific channels, appearing as a cover article in Physical Review Letters, one of the most selective and highly regarded physics journals in the world, a publication venue that requires independent expert peer review before any paper is accepted. Specifically, the kind of institutional scrutiny designed to catch exactly the sort of overstated or unsupported claim that a less rigorous announcement might get away with. So where does all of this leave the honest, complete answer to the claim in your headline? Zuchongzhi 3. Zero genuinely, verifiably outperformed Google's Sycamore chip by a factor of 1 million on a specific, deliberately quantum-favoring benchmark task. A real, peer-reviewed, published result from a serious, credentialed Chinese research team, not an exaggeration or an internet rumor. That comparison specifically involves Google's older 2019-era chip rather than its newer Willow processor, against which Zuchongzhi 3. In Zero's performance looks more like genuine, closely matched competition than a clean victory in either direction, with Willow actually holding a slight edge on certain individual precision metrics, even as both chips post staggeringly large advantages over classical supercomputers on their respective benchmark tasks. And like every major quantum supremacy claim that's come before it, stretching back to Google's original 2019 announcement, this result should be understood honestly as a snapshot of where quantum hardware currently stands relative to classical computing on one specific, narrow, deliberately challenging benchmark, rather than a final, permanent verdict on which country or which company has definitively won the broader, still very much ongoing race to build genuinely useful, general-purpose quantum computers. A race that, based on the pace of announcements from Hefei, Santa Barbara, and labs elsewhere around the world over just the past year alone, shows absolutely no signs of slowing down anytime soon. Let's dig a little deeper into exactly how the hardware differences between Zuchongzhi 3.0 and its predecessors made this leap possible, because the underlying engineering story is genuinely worth understanding on its own terms. Moving from Zuchongzhi 2's 66 qubits to Zuchongzhi 3. Zero's 105 qubits isn't simply a matter of bolting on more components. Every additional qubit you add to a superconducting quantum processor increases the overall complexity of the control electronics needed to precisely manipulate each one, increases the physical space available for stray electromagnetic interference to creep in, and increases the number of individual components that need to maintain extremely high fidelity simultaneously for the overall system to function reliably. The USTC teams reported improvements in gate fidelity, despite this considerable increase in scale, reflect genuine progress in exactly the kind of unglamorous, detail-oriented engineering work. Better materials, more precise fabrication, improved control electronics that tends to get glossed over in favor of the more dramatic headline speed numbers, but that actually represents the harder, more foundational half of what makes a result like this possible in the first place. The specific shift to tantalum and aluminum construction, bonded through an indium bump flip chip process, deserves a bit more explanation, because it reflects a broader trend that's been playing out across the entire superconducting quantum computing field over the past several years, not just at USTC. Tantalum, in particular, has emerged as an increasingly popular material choice among leading quantum hardware labs because it tends to form a more stable, less lossy oxide layer on its surface compared to some of the materials used in earlier generations of superconducting qubits, and minimizing these kinds of surface losses is one of the most persistent, stubborn engineering challenges standing between current quantum hardware and the kind of long, stable coherence times that future, larger-scale quantum computers will eventually need. The flip chip bonding process, referenced in USTC's paper, essentially a manufacturing technique that allows different layers of a chip's circuitry to be precisely stacked and connected using tiny indium bumps rather than more traditional wire bonding methods, is similarly part of a broader industry trend toward denser, more precisely controlled chip architectures, one that both Chinese and American quantum hardware teams have been independently converging on, as they each search for ways to scale up qubit counts without sacrificing the delicate fidelity each individual qubit needs to maintain. It's also worth taking a closer look at exactly why random circuit sampling has become such a persistent, recurring benchmark across essentially every major quantum supremacy announcement from every serious lab in the world, because understanding its specific appeal to researchers explains a lot about why this exact comparison keeps showing up again and again in headline after headline. Unlike many potentially useful quantum computing applications, which often require solving problems where the correct answer needs to be independently verified through some other means, random circuit sampling has a mathematically elegant property that makes it particularly well suited as a clean, unambiguous demonstration of quantum advantage specifically. The statistical properties of the output distribution can be checked against theoretical predictions using cross-entropy benchmarking, a technique that lets researchers verify with reasonable statistical confidence that their quantum processor is genuinely producing the correct kind of quantum mechanical output rather than something that merely looks superficially similar, without needing to actually solve the full, intractable classical simulation problem to check every individual answer. That technical property is exactly why this specific benchmark, despite its genuinely narrow practical usefulness, has become the closest thing quantum computing has to an agreed-upon, standardized speed test, the equivalent of a specific, universally recognized track and field event that different countries' Olympic teams keep training for and comparing results against, even though excelling at that one event doesn't necessarily translate directly into being the best team across every other event in the broader competition. There's also a genuinely important and often underappreciated verification dimension to this specific story worth spending time on, because it addresses a completely reasonable question a skeptical viewer might have. How do we actually know these results are real, rather than simply taking a research team's word for it? Beyond the peer review process itself, which subjects a paper like this one to scrutiny from independent expert reviewers before publication, results like Zuchongzhi 3.0 zeros have also been subject to exactly the kind of public, cross-institutional scrutiny that characterizes legitimate scientific competition, rather than the closed, unverifiable claims that characterize the various fabricated internet mysteries we've covered in other contexts. When Google's earlier Sycamore claim faced a credible classical algorithm challenge from IBM back in 2019, that challenge was published, argued over publicly, and became part of the permanent, citable scientific record surrounding that original claim, exactly the kind of open, adversarial, self-correcting process that gives the field's overall body of published results real credibility over time, even when any single claim within that record eventually gets partially revised or narrowed. Zuchongzhi 3.0 E0's results, published in a similarly rigorous, publicly accessible journal, are subject to that exact same kind of ongoing scrutiny from the broader international physics community, including researchers at Google, IBM, and other competing labs who have every professional incentive to carefully check a rival team's math and publish a rebuttal if they find a meaningful flaw in it. It's worth closing with a broader reflection on what this specific back and forth, Sycamore then Willow then Zuchongzhi 3. Zero's million times comparison against Sycamore specifically, then the ongoing closely matched rivalry against Willow, actually tells us about the state of the entire quantum computing field right now, because I think it's a more interesting and more optimistic picture than a single China beats America or America beats China headline framing tends to capture. What we're actually watching, in close to real time, is two of the most sophisticated, well-funded, seriously staffed research programs on the planet, one based in Hefei, one based in Santa Barbara, pushing the exact same fundamental hardware approach, superconducting qubits, forward in parallel. Each learning from and responding to the other's published results, each posting genuinely significant, independently verifiable milestones roughly every few months, in a sustained, high-stakes competition that's producing real, tangible scientific and engineering progress at a pace that would have seemed almost unbelievable even 5 or 6 years ago. Whether the next headline-grabbing announcement comes from USTC, from Google, from IBM, or from any of the other serious labs working on entirely different underlying qubit technologies, this specific, well-documented million times comparison between Zuchongzhi 3.0 and Google's Sycamore chip is a genuine, verified data point in that larger, ongoing story, one worth understanding accurately and in full context, rather than either dismissing it as exaggerated hype or treating it as some kind of final, decisive verdict in a race that, by every available piece of evidence, is still very much underway. If there's one useful habit to take from this story, beyond the specific numbers themselves, it's this. When you see a headline comparing two quantum computers, ask which specific chips, on which specific benchmark, at which specific point in each company's timeline. Those details aren't pedantic footnotes, they're the entire story. A million times advantage over a 6-year-old chip and a genuine, closely matched rivalry with a 5-month-old one are both true at the same time, and both are worth knowing, because together they tell you something a single headline number never could. That this race has no permanent winner yet, only a series of remarkable, well-documented leapfrogging results, with the next one likely already underway in a lab somewhere, waiting for its own turn to become next year's headline. It's also worth stepping back and considering what this specific rivalry means for the broader question of where quantum computing, as a field, is actually headed over the next several years, because the pattern visible in the Sycamore to Willow to Zuchongzhi 3.0 sequence tells a genuinely encouraging story about the pace of progress, even independent of who happens to be ahead at any given moment. Each of these headline announcements has arrived closer together than the one before it, Sycamore in 2019, Zuchongzhi 2. One in 2021, Willow and Zuchongzhi 3.0, both within a few months of each other in late 2024 and early 2025, a compression of the announcement cycle that suggests both the American and Chinese quantum computing programs are iterating and improving at an accelerating rate, rather than the field settling into a slow, predictable, incremental pace, the way some more mature areas of computer hardware development eventually do. That acceleration is itself a meaningful signal, independent of any single-speed comparison, because it suggests the underlying engineering challenges standing between today's noisy, limited quantum processors and tomorrow's genuinely large-scale, broadly useful quantum computers are being worked through at a pace that continues to surprise even people who follow this field closely. There's also a fair, worthwhile question about what all of this competition ultimately means for anyone outside the small circle of researchers actually building these chips, since neither Zuchongzhi 3.0 nor Willow, however impressive their benchmark results, are anywhere close to running the kind of practical, everyday applications that tend to get discussed alongside quantum computing's long-term promise: drug discovery, new materials, breaking or defending modern encryption. Both Google and USTC's own researchers have been notably candid on this point in public statements, generally describing genuinely commercial, widely useful quantum computing applications as still being years away, likely sometime in the 2030s under most credible expert timelines, even as the underlying hardware milestones continue arriving at an accelerating pace. That's an important, honest caveat to hold alongside the excitement of any individual speed comparison, and it's exactly the kind of grounding detail that distinguishes a careful, accurate account of this rivalry from the more breathless, headline-only version that tends to circulate without any of the surrounding context attached. Taken together, that's the complete, honest shape of this story. A real, peer-reviewed, independently verifiable result, a serious and increasingly fast-paced competition between two of the world's most capable quantum computing programs, and a healthy dose of realistic context about how far the field still has to go before any of these remarkable benchmark numbers translate into something the rest of us will actually use. All three of those things are true simultaneously, and understanding them together, rather than settling for whichever single number happens to be in the headline you clicked on, is exactly what it takes to actually follow this genuinely fascinating race as it continues to unfold.